title of my talk is Half Metallicity in Chromium Aluminum Terminated Cobalt to Chromium Aluminum Film. I'm Pavel Lukashev, and I work at the University of Northern Iowa. So I will start with a brief outline of my talk, and I will start with acknowledgements. Then I will spend a minute or two talking about motivation behind this work and background. So then a minute or two on the methods. So this is a computational work, so I will talk about the codes that we use to do these calculations, and I will talk then about this material, cobalt to chromium aluminum, in two geometries. So I will discuss bulk properties of this material and thin film properties. And then I will finish with brief conclusions. So let me start with acknowledgements. So the work was done by, most of the calculations are done by two students working at UNI, Juliana Herran and Ryan Carlisle. And the work is done in collaboration with Dr. Parashu Hara from South Dakota State University. So also I acknowledge the financial contribution of UNI Summer Fellowship and Geraldine Teman Fellowship, which supported students working with me this past summer. So let me start with a brief introduction. So what is the motivation behind this work? The material that I'm going to discuss is half metal, and half metal is a material that is 100% spin polarized. So it has energy band gap for one of the spin channels, and it's a conductor for the other spin channel. So these kind of materials are in particular demand in spin-based electronics, known as spintronics. And so the high degree of spin polarization in electron transport is one of the cornerstones of spintronics. And half metals, they can provide not just a high degree of spin polarization, but ideally 100%. There are, of course, different mechanisms that can destroy the 100% spin polarization, and among them are mechanical strain, atomic disorder, temperature, and termination surface interface. So this termination surface and interface I'm going to discuss later in this talk. And the material that I'm going to talk about is a Hölzler compound. Many Hölzler compounds are reported to show half metallic properties, and they are particularly attractive because they have a very high Curie temperature. So when I say high Curie temperature, in most of the reported cases, it's much larger than room temperature. So the cobalt to chromium aluminum is one example of Hölzler compound that was reported in the past to exhibit bulk half metallic properties. And this is the material we decided to study. Also, in this lower right corner, I will keep a reference to the paper that covers all the details of this talk. So the computational resources that we use for this work, so the software is basically this is a regular density functional calculation, and we use VN ab initio simulation package. The calculations, to run these calculations, we use two hardware resources, a local computer of UNI physics department, and we also did the part of the calculations on Pittsburgh Supercomputer Center's cluster called Bridges. So okay, let me get to the results then. So here on the left you see a crystal structure, a unit cell of cobalt to chromium aluminum, and this is a typical cubic Hölzler structure. So the cobalt atoms are shown in blue, chromium red, and aluminum in greenish. So then on the right hand side you see a plot of the densities of states of this material in the bulk geometry. Right? So if we look at this figure, we can clearly see that the minority spin is semiconducting, and the energy gap is about 0.5 eV. At the same time, if we look at the densities of states for the majority spin, we can clearly see that there are states on the Fermi level, so this material is a conductor for the majority spin. So this is, of course, a typical picture of a half metallic electronic structure, right? So what is the next step? So for many device applications, so one wants to look at the properties of material in what is called reduced geometry or thin film geometry. So that was the next step of our study. So we constructed this supercell shown here on the left-hand side of the figure. So essentially what we have here is 3 unit cells of this material stacked in 0, 0, 1 direction. Right? And here we have 2 different terminations. So here we have chromium aluminum termination, and at the top we have cobalt termination. And these two termination surfaces are separated by a vacuum layer. And then we look at the cell-resolved densities of states for this material. So here, so on the top left corner, we see the total densities of states of this entire cell. And if we compare it with the one we just discussed for the bulk structure, we can clearly see that the half metallicity is destroyed. So here in the band gap, we have certain states. And so close inspection shows that these states are mostly coming from the cobalt. So they are mostly blue, so they are coming from the cobalt. So then let us look at the cell-resolved densities of states. So here we have a figure of the density of states for the middle cell. So the middle cell is here, and we clearly see that it resembles almost perfectly the electronic structure of the bulk material. And this is a relatively good news. It shows that the size of the cell is adequate to describe the behavior of this material. Right? So the middle cell is essentially a bulk-like. So then next, let us look at density of states of this material for the chromium-aluminum termination and cobalt termination. So let's start with cobalt termination. So this bottom right corner. So we can clearly see that the half metallicity is destroyed here because of the presence of the cobalt states, right? So these blue states over here that emerge in the energy gap of the minority spin. Right? So then we look at the other termination of this material, chromium-aluminum termination, and here comes the one of the main results of this work. So here we can see that for chromium-aluminum termination, the band gap for minority spin is retained. So we still have a band gap. It is probably slightly smaller than for the bulk, but we clearly can see that for chromium-aluminum termination, we still have a perfectly half-metallic structure. Right? So what we did next, we considered more or less the same cell, but with chromium-aluminum termination on both sides. So practically speaking, we just basically removed the layer of cobalt from here. So first, this was done to check the stability of the system. And second, we wanted to check the half-metallic properties of this material by looking at the magnetic structure. So let me show you the results. So this is the second set of calculations. Again, almost identical to what I showed you on the previous slide. But here we don't have cobalt at the top. So we have a symmetric termination, chromium-aluminum here, chromium-aluminum here. And now let's look at this. So top left corner shows the density of state calculated for the entire cell. If we go back, right, so this is the same calculation done with one additional cobalt layer. So we can clearly see the difference, and this is again one of the main results of this work, right? So here we have, this is again total density of state, and here we see states, additional states that appear in the minority spin channel. And then next slide, same calculation, total density of state, entire cell. We just remove one layer, and that states disappear, right? So this shows that so detrimental effect on half-metallic properties of this material is essentially entirely due to the presence of that cobalt layer. So then we also looked at, so we did similar analysis. So we looked at cell-resolved densities of states for this material. So this is total, and here we have middle cell. So again, not surprisingly, it retains the half-metallic properties. And here we have chromium-aluminum termination. So the one shown here, and then this is chromium-aluminum termination of the top cell. They are all more or less identical. Not surprisingly, the only difference here is that the number of cobalt states is reduced for this top cell, but this is not surprising. We just removed one layer of cobalt, so we just get a reduction of the number of states of cobalt, right? So then what is the main, before I jump to the next slide, what is the main conclusion here? So if this material can be synthesized in thin film geometry, and if it can be synthesized with chromium-aluminum termination, potentially this material should behave as a thin film half metal. And there are not that many reports of thin film half metallicity in the literature. So next we look at the magnetic structure of this material. So here I have atom-resolved magnetic moments. I'll skip the table, but I'll just quickly comment that we calculated total magnetic moment for the thin film cell with cobalt termination and without cobalt termination. So on the for the cell with the cobalt termination, we get a total magnetic moment, which is non-integer. And for the chromium-aluminum terminations only, we get a total integer magnetic moment for the entire cell, which is another indication of half-metallic properties. So then we also looked at how the electronic structure of this material changes under influence of external pressure and strain. So first, so this slide shows evolution of density of states of this material under uniform pressure, and all calculations are done for bulk geometry. So the ground state lattice constant of this material is approximately 575. So then we consider both compression and expansion of the cell, and as we can see, this material more or less retains its half metallic properties for the compression, for the entire range of considered compression, and also for decent interval of expansion. Again, we're talking about uniform pressure here, right? Eventually, half metallicity is destroyed when the cell is expanded beyond certain limits, right? So here in red circles, we plot spin polarization, so we can clearly see that it is 100% up to certain lattice constant, and also we plotted total magnetic moment. So total magnetic moment is integer, again, which is another indication of half metallicity, up to certain lattice constant, and this interval includes the ground state lattice constant, which is 5.70 something, right? But if we're looking at device applications of this material, then usually uniform pressure is not a realistic scenario. So one has to look at how the electronic structure of the material changes under biaxial strain. So next we'll look at the properties electronic structure of this material under biaxial strain. So the plot is shown here. So biaxial strain, so we optimize the out-of-plane lattice constant for each in-plane lattice constants, and then for each optimized geometry we calculated the electronic structure. So the figure is shown here, and again very good news. So we can see that the half metallic properties are retained for more or less entire range of considered biaxial strain. So here we have a plot of the density of state for various in-plane lattice constants. And here we plot the C over A ratio, and the important figure here is shown at the top right. So it shows spin polarization and calculated magnetic moment. So we can clearly see that the spin polarization is 100% for more or less entire range of considered biaxial strain, except for very, very strong in-plane compression, right? So this last data point over here. So this one more time indicates that this material may be very useful for thin film applications in spintronics. So again, for certain termination, chromium aluminum termination, it retains half metallic properties, and these half metallic properties survive a very large range of biaxial strain. Right? So that's it. So let me just finish with quick concluding remarks. So we looked at the cobalt to chromium aluminum, which was reported in the past to be a half metallic material in the bulk geometry, and we considered how the properties of this material change in thin film geometry. So we looked at two possible terminations: cobalt termination and chromium aluminum termination. So for cobalt termination, this material, so the half metallic properties of this material are destroyed, and at the same time for chromium aluminum termination, so the half metallic properties are retained. So we get 100% spin polarization even in thin film geometry if the thin film is terminated with chromium aluminum surface. So then again, main conclusion of this work is that chromium aluminum termination of this material is half metallic in ground state, and not only in ground state, but also under influence of a relatively large biaxial strain, so both compressive and tensile. So again, these are the main conclusions of the talk. Here is a reference. So again, most of the work was done by two students at UNI, Juliana Herran and Ryan Carlisle, and the work is done in collaboration with a colleague from South Dakota State University, Dr. Parashu Harel. And here is the reference to the recently published paper. Thank you.